All right, let's jump right into this explainer and uncover the microscopic drama of chemical bonding. At its core, chemistry is really just a story about how atoms settle their differences. They have needs. Specifically, they absolutely need full electron shells to achieve stability. And, well, they don't always get along when trying to fulfill those needs. So today, we're going to explore the fascinating world of how they actually manage to compromise. Here's our roadmap for today. We'll start with the art of sharing, move into drawing the invisible, navigate the electronegativity tug-of-war, look at how shape completely determines function, and finally end with the incredible story of the chemist denied a Nobel Prize. Section 1. The art of sharing. Let's look at the fundamental problem these atoms face: incomplete electron shells. When they're missing electrons, they're unstable. But how do two atoms resolve this if neither of them is willing to just hand over their electrons? Well, the answer is they compromise. When atoms like, say, two hydrogens or two chlorines bump into each other and neither can pull electrons completely away from the other, they share. This forms what we call a covalent bond. By sharing a pair of electrons, both atoms essentially trick themselves into seeing a full shell. The shared electrons are attracted to both nuclei at the exact same time, holding the whole thing together in a stable mutual arrangement. And this sharing, it can actually scale up in some pretty wild ways. Atoms aren't limited to just sharing a single pair of electrons. Take a look at a single bond found in hydrogen gas, where they're sharing just 2 electrons, and compare that to a triple bond in nitrogen gas, sharing a massive 6 electrons. The difference is night and day. Sharing more electrons actively pulls the atoms closer together. The result? That triple bond is significantly shorter and just incredibly strong. It's literally the reason why the nitrogen gas we breathe every day is so stable and difficult to break apart. Let's move on to section 2, drawing the invisible. So now that we know atoms share, how do we actually picture it? Since molecules are unimaginably small, we need a reliable way to map them out. We use a simple but super powerful visualization tool known as Lewis structures. Think of them as basically an architectural blueprint for molecules. We use dots to show non-bonding pairs of electrons, we call those lone pairs, and lines to represent the actual bonds. This lets us predict exactly where electrons live and how the atoms connect. The crucial trick here is just following a very logical step-by-step method. Take water, for instance. First, you count the total valence electrons for H2O, right? That's 8 total. Second, place oxygen right in the middle. Third, connect the hydrogens with single bonds, which uses up 4 of those electrons. Fourth, you distribute the remaining 4 electrons as 2 lone pairs on the oxygen atom. And finally, check your work. Oxygen has its full 8, each hydrogen has its necessary 2. Boom! Everyone's stable. All right, section 3, the electronegativity tug-of-war. We've got our 2D blueprint figured out, but here is a major plot twist. Sharing electrons, as it turns out, is almost never a perfectly equal 50-50 split. Enter electronegativity. This concept essentially turns a peaceful sharing agreement into a literal, microscopic tug-of-war for electrons. It's simply a measure of how strongly an atom attracts those shared electrons toward itself. And frankly, some elements are just way greedier than others, with fluorine being the absolute greediest element on the entire periodic table. And this tug-of-war plays out on a spectrum. If the electronegativity difference between two atoms is practically 0, they share equally. We call that a nonpolar covalent bond. But a moderate difference? That creates a polar covalent bond. One atom starts hogging the electrons, like oxygen does in water. It pulls the shared electrons much closer to itself, giving the oxygen a slight negative charge and the hydrogens a slight positive charge. Now, if the difference is huge, the sharing breaks down entirely, resulting in an ionic bond where an electron is just completely stolen. Section 4, how shape determines function. Let's see how all this builds together, because molecules, they aren't just flat two-dimensional drawings. They exist in complex 3D space, and shape changes absolutely everything. This brings us to VSEPR theory. It's a big acronym for a really simple idea. Negatively charged electrons hate being near each other, so they repel to get as far apart as mathematically possible. This repulsion dictates highly specific shapes. For instance, water has 4 electron groups total, but remember those 2 lone pairs we drew earlier? Those lone pairs push down hard on the bonding pairs, forcing the water molecule into a very specific bent shape. Which brings us to a fascinating paradox that I really want you to consider. Both carbon dioxide and water are made of 3 atoms, right?
And both molecules contain polar bonds where atoms are playing that tug of war. So why does carbon dioxide act totally nonpolar while water acts like a highly polar molecule?
The answer comes down entirely to shape. Structure determines function. Carbon dioxide is linear. The oxygens pull on that central carbon in perfectly opposite directions, so the pulls just cancel out completely, exactly like a tied game of tug of war. But water is bent. Those two hydrogens are angled downward, so the polarity doesn't cancel out. Instead, it adds together, creating a strongly polar molecule. And that single structural reality gives water its unique properties. It literally dictates how all biological life on Earth functions. Finally, Section 5, the chemist denied a Nobel. Let's step away from the atoms themselves for a second and ground this beautiful science in the human history of the architect behind these molecular blueprints. Back in 1916, Gilbert N. Lewis completely revolutionized chemistry. He's the guy who proposed this entire electron sharing model. He invented those simple dot diagrams that every chemistry student and advanced researcher still relies on over a century later. And beyond that, he revolutionized thermodynamics and acid-base theory. He is undeniably a titan of modern science. Yet, despite his foundational contributions to our understanding of the universe, there is one truly staggering number associated with his legacy: 35. That is the exact number of times Gilbert N. Lewis was nominated for the Nobel Prize in Chemistry. And how many times did he actually win? 0. Not even once. This fact remains one of the great controversies in the history of science. And honestly, it leaves us with a lingering, provocative thought. We completely rely on these brilliant models to understand the very fabric of our reality. But why do some of the most critical structural foundations of our universe go completely unrewarded by the institutions meant to celebrate them? It really makes you wonder, who else in history has built the blueprints we rely on today entirely without recognition?